The speaker is joining in 2 minutes. Actually, she's facing some issue regarding the Zoom. She's joining in 2 minutes.
Hello. Hello. Am I audible?
Yes, Pooja.
Yeah. Hello, everyone. Today we are having this second episode. Um, like the speaker would be joining us in a few minutes. So, would you like to introduce yourself? We have few participants here. Drishti, Jain, Amit, Vikram. Would you guys like to introduce yourself in the meantime? Karan Akbari, Hemant, Anusha.
Hello.
Yes. Hello.
Hello, myself, SM
Hello.
Heman.
Hello, the admin sir. Actually, Mami is facing issue in joining the meet because like she does not have the IIT Madras mail. So what can we do regarding that? Pooja, yeah, please continue.
Yeah, Hemant, you were saying, please introduce yourself.
Hello, myself Shekhamanti Heman, and I'm from Jamshedpur, and I'm currently working in a steel company as an electrical maintenance. And I'm interested in astronomy and astrophysics, as I would like to pursue a career as a data scientist or data analyst in astronomy field.
Thank you, Hemant, for introducing yourself. Others, would anyone come forward to introduce yourself?
I am Karan.
Hello, Karan.
Yes, I am actually doing my bachelor's in physics and would like to continue it in astrophysics. I'm a master's in astrophysics. So I'm working for that, and I'm from Jamnagar, Gujarat. I'm currently studying in Central University of Rajasthan.
Thank you, Karan, for introducing yourself. Others, oh, there are few participants here. Yeah.
Hi, this is Anusha here.
Hello.
So I am an electronics engineer with 3+ automobile industry.
Hello, guys. So yes, the problem is resolved. The host and the speaker are joining in 2 minutes. So please be with us.
Yeah.
Yes, Pooja, you can start. So we have with us Survi ma'am. Yeah, Pooja, please continue.
Sorry for the inconvenience, everyone. There had been some technical issues, but now we're ready to kickstart this session. So, good evening, everyone. I'm Pujashri. I welcome you all to the second episode of Nilgiri Narratives, a talk on astronomy and computing. The huge success of the previous episode has been a true motivation for us. Today, we have another amazing guest with us. It is my pleasure to be here today and introduce our esteemed guest speaker, Dr. Surbi Agarwal. We are fortunate to have her here to share her insights and expertise. Dr. Surbi Agarwal is working as an associate professor in the Department of Computer Science at Rashtriya Vidyalaya, Bangalore. She has done her PhD from PESIT Bangalore South Campus under Vishveshwaraya Technical University, Belagavi. She has 15 plus years of extensive teaching and research experience in institutes like PES University, IIT, Pune, the Yanand Sagar University, etc. Her area of research includes machine learning, data analytics, soft computing, and human-computer interaction. She has conducted various student training programs on big data analytics with Hadoop, machine learning, and advanced databases. She has published several articles in international journals and conferences, including SEI journals. She has also served as a reviewer of papers and articles of some reputed conferences. We welcome you, ma'am. Thank you so much for joining us. Right now, I'll take a step back and let Surbi ma'am take it from here.
Yeah, thank you, Pooja. And thank you, Vishak, for inviting me for this particular session. So basically, initially, I would like to welcome you all for this particular session and would like to say again, thanks a lot. So in this particular session, basically, I'll be introducing you how computational aspects basically are implemented in the astrophysics domain. Basically, as Pooja told or give my introduction, so my PhD or my research work was in astrophysics domain, and we worked with Indian Institute of Astrophysics, which is at Kormangla in Bangalore. It's a government, our Indian government office. So where we worked in with those people in order to get the domain knowledge and other things to do our work, to carry on our research work. So we have, as you all know, that right now basically the environment is like, because of the introduction of machine learning techniques and data analysis, statistics, tools and techniques. Right now, we are actually into the era of, you can say, multidisciplinary research oriented platform, and that's what basically we also did. We, instead of going for really core algorithms, we actually worked on core algorithms and new computational methods also in order to solve the problem, but we choose the domain as astrophysics. Why? The reason is that the particular topic which I selected was very fascinating, and I had an interest from my childhood in that particular area. So to start with, where basically we will have the applications, various applications of machine learning in astrophysics. So can I ask any one of you if you have any knowledge about where we implement the computer science and engineering aspects into the machine learning aspects into the astrophysics domain? Anyone have any idea? Yeah, the student competitive present over here. If you would like to tell anything. Image processing. Okay, it is one part of it, yeah. But do you know what are the different domains and where we are actually implementing all these things? Image processing, machine learning, your CNN, deep neural networks and all. Do you know for what reason actually they need us? Analyzing patterns. Yeah, somebody's writing analyzing patterns, galaxy clustering. Okay, orbital prediction. Fine. Yeah. so we have many more applications basically present in the astrophysics, where we use the computational sciences and these particular disciplines. So to start with, use of applications like metrica to find new celestial objects. Yeah, so as he wrote, to find new celestial object, I'll little bit talk about that also today. So, you know, we are far, far, far away from millions of galaxies, stars, planetary systems, and all these things, right? So we do study of those particular things which are several light years or billions or millions of light years far away from us, right? So I would like to start with a few applications I will name. I will also name a few, as you people have written few, like galaxy clustering, orbital prediction, applications like finding a new celestial objects. So in addition to that, recently the work is more going on towards which direction? One of the work which is going on in galaxy direction, galactic data, where we study different types of galaxy formations, how these galaxies have been formed, right? What is it actually helps us to predict the age of our universe also, right? We have several other celestial objects like quasars, pulsars, neutron stars, binary stars, black holes, supernova, and all the others, right? So astrophysics, basically universe is very big. So astronomers keeps on doing research in different areas, like which is actually helping us. One such interesting, two such case studies basically I'll be discussing with you people today, and will tell you how computer science has been involved over here in these particular areas. So one such problem is of finding the or determining the habitability of the exoplanets. So before going into the depth of what is habitability of exoplanets and all, anyone who knows what do you mean by an exoplanet? You might have heard about planets. We have 8 planets in our solar system. So have you heard about exoplanets? Exoplanets are planets, yeah, that might have life. No, it's not this. So we have several answers now here. Yes, somebody has written planets which are outside our solar system. Yeah, exactly. Those particular planets which are outside our solar system, they does not belong to our solar system, but they belong to our own galaxy. Okay, because we cannot do the study of, there is no use of right now doing the study of very far off galactic extrasolar planets. Reason is that anyways you cannot reach, right? So and feel free to interrupt in between and to have discussions. Okay, so yeah, so thing is that these exoplanets, or we also call them as extrasolar planets, are outside our solar system, right? And we do their study. So what are the reasons we do their study? First of all, we want to know that are there any planets which are habitable? So finding the habitability is a very complicated question, very complicated thing. We need to consider several factors, like how the atmosphere of that particular planet will be, whether there is a chances that liquid water exists there or not. So many questions they have to find out. Before finding all these questions for these exoplanets, again comes the question of identification of these particular exoplanets. Like how to identify whether a particular celestial object which we are watching from here is actually a planet or it is some another planet. So we have two aspects here in the study of exoplanet. One is their classification. Classification can be done on various aspects. I'll show you some data set also with respect to this. So classification can be in terms of various aspects. Similarly, you have the identification problem also. So though astrophysicists are actually reading the data, cosmological data from their telescopes, which are very, very high resolution telescopes right now, like Large Synoptic Survey Telescope, LSST, we call it. So if little bit of aperture also can actually cover a huge part of sky, and once that particular part of sky itself contains huge amount of data, bulk of data, and it is very, very complicated for them to understand this data, to analyze this data, to see that this particular celestial object, what they are watching, is it extrasolar planet or something else, right? So in order to detect basically these extrasolar planets, our scientists or astrophysicists, they use certain methods. Some of the names of such methods are radial velocity method. So another is astrometry, direct imaging method. Then you have one very famous method through which most of the extrasolar planets have been identified. We call it as transit method. Little bit I will tell you about the transit method. So in transit method, what happens? That, for example, our sun is there, right? And how they detect basically. So for example, our sun is there. Sun is our star of our solar system. And we have these 8 planets which are orbiting a particular star. So when they observe it from their telescope, what they see, they read certain light curves. Light curves are basically the data. Yeah, is there something? Anything, any question or something? Okay, so these light curves basically are the plot shows the continuous is coming in, right? So what these continuous radiations are basically showing us, that continuously a particular planet is transiting that particular sun. So when where your telescope is focused, in between the study of that star or light of that star and telescope, if after a particular point of time, uh, any issue or anything?
No, ma'am, it's just the members joining, ma'am.
Okay, fine. That sound is fine. Yeah, okay, fine. So what happens that when a particular planet pass through that star and comes in between the light from that particular star and between the telescopic data, there is a dip in the light curve. I would like to show you that particular picture here. So just 1 minute, let me share the screen and let me open that curve. Is it visible? Have I shared the screen? 1 minute.
No, ma'am.
Yeah, 1 minute. I'm sharing the screen. Is it visible now?
No, ma'am. Still not.
Yeah, I think that the window it's not picking. Just a moment. Anyone has something like some photo how to show, like it's in JPG format?
Ma'am, you can share with me. I would try to share this.
Okay, sure. So I'll be sharing with Vishak. Yeah, Vishak, I have sent you.
Yes, ma'am. Just a second.
Yeah, this we don't have, I think, full screen. Yeah. Yes. So you can see this particular image. So here you can see that these red color and black color ones, what exactly it is showing. These are showing the continuous light coming from the star. So you can see in between breakage is there, right? So that particular breakage might be due to some disturbances or something. Otherwise, there is a continuous wave which is coming in. Whenever in this continuous waveform, we see a dip. Can you see a dip in between V-shaped, right? So when we see a dip over here, so yeah. So when we see the dip over here, what we actually know that there is a particular object which the light coming from that particular star to the telescope. So that's why telescope is unable to read properly the light source over here coming from the star. And when this pattern repeats, what we say that, yeah, there is a dip, it means that there is a particular movement which is happening in between at after a particular time interval, and hence we identify that usually what happens that stars have their own planetary systems and their planets revolve around their orbit, and at a particular time of interval this dip basically will be produced, and hence we identify or detect that it's a planet. Problem we have in the transit method is transit photometry method, we call it. So problem with this particular method is that we have something called as eclipse binary system, twin binary system. What basically the twin binary system is that we have certain times two stars which are actually spinning around each other. Okay, so certain stars, all like for example, our sun is having 8 planets. Like that, some of the stars are there with no planets. Some stars are there with 1 or 2 planets, right? So it depends. So in twin binary system, what happens that we will have usually 2 stars, and both the stars used to spin around each other, right? And certain times it confuses us to identify that yes, it is a planet, because here again one particular star's light at a regular time interval is getting hindered by the another particular star which is revolving around it. So that's how then we sometimes classify wrongly that particular star as the planet. So this is the problem with the transit method, and hence we have certain other methods which are used by the astrophysicist in order to detect that it's a particular planet. So here in the detection of these particular planets itself, we have various computational algorithms which are working together in order to perform this particular detection. Yeah, Vishak, you can close this. Thank you. Yeah. So that's what basically we have issue in these particular systems. Most good method, what we call it as actually the radial velocity combined with the transit method used is what they follow. But again, certain times it is not able to classify due to some other cosmological phenomena, and hence we apply different algorithms, different computational algorithms using the machine learning. Sometimes signal to noise ratio is one particular aspect through which we try to identify, and we write our algorithm based on that. Certain times wavelet transform and other things are there through which we extract the features, do the study of those features, and say that it's a planet. So this is one particular aspect where computer science and engineering help astrophysicists to identify that it's a planet. For the planet identification itself, NASA has launched several missions, several planetary missions. Like for example, NASA has launched initially Kepler mission in 2010 to identify that it's a particular type of, it's a planet, right? So they say that it's a Kepler object of interest and it's a particular type of planet. So they basically this mission they launch in order to find the terrestrial plane, right? So terrestrial plane means they try to find out which are the planets which comes under the habitable zone of a star. So do you know what do you mean by habitable zone of a star? Anyone?
No, actually.
Yes?
No, I don't know.
No, okay. So one or two people have written Goldilocks. Can you elaborate little bit, Mohit? Earth is in the habitable zone of our solar system, but what do you mean by exactly habitable zone? The region around the star where life can arise, zone with ample. Yeah. So Bipin has written something. I hope you are not Googling or doing something. So Bipin has written something. Zone with ample climatic conditions for life to sustain, or where liquid water can exist. So these are certain criteria. Every star has a habitable zone wherein the temperature is such that a planet can have suitable conditions for life. Okay, so it means that the atmosphere will be proper, your oceans will be tidally locked. You know, every planet has its own oceans and all, so oceans will be tidally locked and all. So all those aspects basically astrophysicists basically study. Okay, so we Kepler mission was basically launched in order to identify whether the celestial object is a planet or not, and also to identify whether this planet is within the habitable zone of a planet or not. But habitable zone of the planet says that life may exist. It does not guarantee that life will exist. Okay, so we computer science engineers basically help the astrophysicists to develop such algorithms which can help them in these type of identifications. I'll talk about one such model on which we ourselves have worked, and our model is basically in use with the IIA people, Indian Institute of Astrophysics. So there they are using, and NASA also has recently for this Kepler mission has actually collaborated with them. Another mission NASA basically launched after the Kepler mission was K2. It was in 2018 when they launched this particular mission, where they created the catalog and make it open source for the public to study that. So NASA has itself launched and created the catalog of the extrasolar planets, and based on that particular data we can perform the study. I'll also show you a particular catalog which was from the NASA's archive, developed by NASA Exoplanet Archive. And through this NASA Exoplanet Archive itself, University of Puerto Rico has come up with its own data set. So what was that data set? I'll show you that in some particular time. After this Kepler mission, K2 mission, again NASA has launched another mission which we call as TESS, that is Transiting Exoplanet Survey Satellite. So basically, Transiting Exoplanet Survey Satellite was launched in order to survey the brightest stars in the universe, like which are the brightest stars in the we should say sky within our galaxies. Okay, so one of our stars is our sun, which is in our solar system. We have some other stars, various other stars, I should say, which are also existing. Why we want to find the brightest star? Because more the brightest the star will be, more are the possibilities of finding more and more number of extrasolar planets over there. Okay, so I'll just quickly go through and show you. NASA also has actually sponsored one project. That project we call as SETI project. Anyone who knows about SETI? Aliens. Yeah, it's related to aliens. It's a search for aliens. So basically, we call it as SETI, Search for Extraterrestrial Intelligence. Search for Extraterrestrial Intelligence. And basically, SETI has started or has developed a machine learning tool which we call as Cetizen. I'm just typing here in the chat box, it is Cetizen. Okay, so this is a machine learning tool which basically has been launched. You know, in between, whatever the fund was given to the SETI project was taken back, was removed from it, because what they found that nothing is happening and budget is going. Finally, they come up with certain things, certain radio signals, what they captured, and the studies is still going on that. And they developed their own machine learning tool repository with the help of computer science engineers working all together day and night and on this particular project. So this machine learning tool has been named as Cetizen. What this Cetizen, it uses various pi files, what has been developed by again computer scientists, science engineers. AstroPy, if you have heard about. AstroPy is one such library, open source library, which has used by the Cetizen project, right? Then you have QPy. In order to do the fast execution, they actually use QPy, which is basically for the CUDA programming. If you have heard about CUDA programming, so for parallel processing, we uses CUDA programming, right? So that fast execution can be done, and you know that we have huge data over here from the tiny patch of the sky also. So in order to study that complicated data, complex data, in order to run our algorithms, we make use of the QPy. Okay, otherwise your laptops may crash, may not work properly. So that QPy is basically one such library. AstroPy also has several tools where you can synthetically generate the images if you have less number of images with respect to some data, and you can work with that. Similarly, AstroPy provides you various other tools for visualization and other things for the astrophysical data. Then we have one more such library, which we call as BlimpPy. BlimpPy. So BlimpPy basically is something which work with a very important project, which we called as the so BlimpPy basically work with the Guppy project. So what is this Guppy format data? Guppy file format. It's a file format. So what is Guppy file format? Basically, Guppy stands for Green Bank Ultimate Pulsar Processing Instrument. So basically, it's an instrument which takes the data coming from a pulsar and perform its study. So that's what basically Guppy is, and its file format it makes use of, and it is used in SETI's an important project which we called as breakthrough learning. we call it as breakthrough learning, listening, sorry, not learning, listening project. So we also call it as BL project. So what this breakthrough listening project is, whatever signals are coming in using these particular libraries, the particular tool, ML tool, keeps on listening what type of signal it is, whether any signal or any different sort of signal or synthetically generated sort of signal is coming from cosmos or not. When it listens that particular signal through this Guppy instrument, pulsars are basically those astronomical objects in the sky which generally emits these radio waves, and it can be collected on the earth in the Guppy format by the telescope. So by this Guppy telescope, and hence we named the file format as Guppy file format. So it's for its processing, we basically have computer science engineers have developed this Blim pipe. Okay, and we are actually presently using all these particular PI files in this SETI, which is a machine learning tool for the search of extraterrestrial intelligence. So this is where again the computer scientists are basically helping the astrophysicists. Now I would like to show you one data set which is basically developed by University of Puerto Rico. Okay, so this particular data set has been derived from NASA Exoplanet archive, because directly it is very tough to work with the NASA data. So they have converted it into a CSV file format, and we have this data set. Let me just share. I think it's open my. Yeah. So it's visible to everyone. This CSV file is visible.
Yes, ma'am. It's visible, ma'am.
Yeah. So you can see over here. You can see over here we have. This is basically 2017 data. So you have some of these features available in Kaggle repository also now. Recently, it has been released in the Kaggle repository. Can you see how many columns do we have? How many dimensions do we have of data? So we have approx 65 dimensions present over here, out of which we have the first column as planet name. Okay, sorry. So first is planet name. Then here this is Kepler planet name, what we have given from the Kepler mission. So Kepler mission's given name is also there. Now you can see another is planet's zone class, right? So in which type of zone the particular planet is staying in its star, which type of zone it is staying. So you can see here it is into the cold zone, right? Then hot zone, warm zone, right? So hot, warm, and cold are the three characteristics. So one of the possible classification what we can do on the planets is based on the zone class. Then you have planets mass class. So whether the planet belongs to Jovian class, or we have Neptunian, superterrane, terrane. So which comes under the category of terrane. Basically, those type of planets usually we do the study for the study of the habitability, because our Earth is basically a terrane class. Our Earth belongs to the category of terrane class. So we generally don't do the study of Jovian or Neptunian or other type of planets. We generally go ahead with the study of terrane or sometimes terrane classes of planets. Similarly, next feature, I'm not going to discuss all the features. So another feature what you can see is the composition class. So whether it's a gaseous planet or it's like a liquid based planet, 3 states of matter. So composition class basically belongs to that. Then whether it's a rocky water classes are again what we study. So we study super terrain and terrain. They belongs to rocky or rocky water type of classes. So you can see its zone is hot. It's in the hot zone of the star. So though it's rocky water, super terrain, maybe right now it is not possible for any life to be here because of the hot climatic conditions, but maybe tomorrow it will become, right? So climatic conditions keeps on changing. For example, if due to global warming, our temperature crosses 50, 60 degrees centigrade, we won't be able to survive on Earth, right? So that's what basically we do the study of rocky water, rocky island, any rocky planet, we do the study. Okay, that's what moon is also rocky, and hence we are studying the moon as well for the habitability. But here we are talking about the extrasolar planets. Then we have atmosphere class, again, whether it is hydrogen rich, because actually we generally hydrogen rich or carbon rich classes are the ones which we generally study. Then you can see here, we have given a parameter where we have given the label, or we have been given the labels. Okay, so the labels are, I hope some sort of machine learning everyone knows here. Yes.
Yes, ma'am.
Yeah. So here labels have been whether a particular planet is habitable or non-habitable. So if you will go through this particular label, you will find almost all as non-habitable classes. Okay. So in this data set, if I will go and do the classification based on this, it will be very difficult for me because my result is going to be biased. So here in the habitable class, we have almost all as non-habitable. However, few classes we have psychroplanet, few classes we have mesoplanet. So psychroplanet, mesoplanet, and all are, we have given the name as from the temperature. Okay, so if your temperature is below 50 degrees centigrade, sorry, below 0 degrees centigrade, or we should say minus 15 degrees centigrade, basically we classify them as mesoplanet. If it is beyond 60 degrees centigrade above, then we call it as psychroplanet. Okay, and between 0 to 50, basically we are calling as the mesoplanet. And psychroplanets are the ones where a temperature goes beyond 60 degree and below minus 15 degrees centigrade, it's non-habitable, right? So these are this was very unbalanced data set, because if we will work with unbalanced data set, then our result will be biased. Your machine learning will always show another planet to be non-habitable, right? Because it has most of the data is non-habitable. How it will learn? Most of the planets it is categorizing as non-habitable. Okay, so when we implemented this particular data set, we actually first performed the data pre-processing where we did the data balancing. And for this particular data balancing, we go ahead, perform some Parson window estimation, and we perform the downsampling and oversampling of the data. We balance the data set, and then we worked with this particular data set. Then we have other things, minimum mass, then this is mean mass value, then this is maximum mass, okay, then radius, density, gravity, skip velocity, stellar flux. Stellar flux is very, very important in order to determine the habitability of the planet. So these are actually various parameters. So again, stellar flux, you have minimum mean value of the stellar flux. So when we work, we always work with the mean values of the stellar flux, mean value of the radius, mean or average value of the mass. Okay. The reason was because minimum and maximum value gives you the clue that, okay, for this particular planet, minimum it can be this, maximum it can be this. So we work with the average value or the mean value of it. Similarly, stellar flux is what? For example, our sun is emitting the light radiations. So how much light radiations are basically falling on the earth? right? So that basically tells the stellar flux, and on the stellar flux, most of the habitability parameters are dependent according to the astrophysicists. So I will show you what we worked for over here. This is equilibrium temperature, equilibrium mean temperature. This is also one of the important parameters. I'll just come to a parameter which we use for the habitability study that we call as the ESI value. You can see here. Yeah, just see here. This parameter is in planet's interior ESI value. So ESI basically is the Earth Similarity Index, and Earth Similarity Index lies from between 0 to 1. This is interior value, this is exterior ESI value, and this is surface ESI value. So this is surface is exterior, this is interior, and this is your normal main ESI value. So how we actually considered this ESI value, this was from the domain of the astrophysics. Astrophysicists used to calculate Earth Similarity Index. Earth Similarity Index, basically they uses one mathematical formula in order to calculate that. I would like to use wait. So I would like to use the whiteboard over here. Yeah, so see here how they basically calculated the ESI value. So ESI basically is nothing but we give it like the product of the planetary properties, where we consider some n number of properties of the planet. Here planetary properties means like its radius, mass, escape velocity and all, right? So we actually give it as I is equals to 1, then any particular planetary property, say x, I, of Earth. It is basically the quadratic distance matrix. We can say what they have considered. So for n number of properties, for example, if 4 are there for the 4 properties, its absolute value, weight. This is from the astrophysicist. So here, this is the formula what they use. So how many parameters you want to consider in order to calculate the Earth Similarity Index of any particular planet? We consider that planetary property for that particular planet. For example, if suppose I say radius of a planet, it is one of the planetary property. If I say stellar flux of a planet, so this is another planetary property. So I will use the formula as it will be the quadratic mean of all the planetary properties. So I will use it as 1 minus square root of, then I will write this for radius of that particular planet for which I am calculating, minus radius of Earth divided by radius of that particular planet plus radius of Earth, it's a square. Here will be 1 by 2. And then again here, stellar flux if I have taken, then this flux, again the same thing, minus stellar flux of Earth. Okay. So this is what actually they are actually using for the calculation of the overall ESI. So overall ESI can be taken as the geometric mean of this. Wi represent the weight given for this. So basically what they do, they generally consider only the 4 parameters for the ESI calculation. Those 4 parameters are radius, density, escape velocity, because escape velocity determines the gravitational pull of a planet, and surface temperature. Why surface temperature? Because due to the surface temperature only we can decide whether we can stay or not, right? So these are the 4 parameters which they actually consider. What happens with what problem we have with this particular formula? It is not guaranteed that only these 4 parameters are sufficient in order to determine the habitability of a planet. Okay, ESI does not guarantee the habitability. But if I want this formula to go beyond this n, means this n can be anything, right? So I want to consider eccentricity of the planet. I want to consider the orbital velocity of a planet. Then I have to increase the parameter. And the property of the ESI matrix is that it lies between 0 to 1. If I go on increasing the number of parameters over here, somewhere my ESI will likely to tends to 0. Okay, so this basically makes this ESI, which is developed by the astrophysics, little bit more problematic in order to identify the particular planet as habitable or not, or to find the habitability metric. So what we did, we developed a new model. First, based on these 4 parameters itself, later we come up with another perturbed model where we try to introduce more parameters, like we considered stellar flux, we considered eccentricity, and proved that our model was better because when we increase number of parameters, it worked equally well. So we gave mathematical proofs and all also for that, and we called that particular methodology as what to say? We called that particular methodology as Cobb-Douglas habitability score. Why Cobb-Douglas? Because we developed that particular model from an economics background, Cobb-Douglas model, which they basically use for the other purposes, like they basically use it for what to say? Labor and capital investment. Basically, what we try to do is we try to come up with a optimization problem. So what we proposed was a Cobb-Douglas habitability score, we called it as CDHS, Cobb-Douglas habitability score. Okay, so initially we considered those 4 values and showed that our model also giving the similar metrics what the ESI was giving. Okay, so based on the 4 parameters again, we developed the CDHS score. It was basically a multiplicative model. So radius raised to the power alpha, let me put alpha like, then density again raised to the power some beta multiplied by surface temperature raised to the power of gamma multiplied by escape velocity raised to the power delta. So this was the model what we proposed, and we showed that any number of parameters we can actually increase. Then when we got this particular habitability score, as it does not guarantee the habitability. What we did, we used the KNN classification, KNN classification, K nearest neighbor classification approach, and we got three classes. We created three classes where one class was belong to Earth category, one was again slightly close to Earth category, and one was non-habitable class. So in which we saw that what parameters were falling in the Earth's category were defined as mesoplanet in their data set. So our results are very much similar to the score what the astrophysicists have actually shown in their data set. The thing was that we developed one machine learning model. You need not to do the whole exercise again and again. Whereas in order to generate the form of data what we have seen in the CSV file, astrophysicists have to do lot much of exercise. Another thing, this model what we proposed is actually extendable to any number of parameters. So this was our one of the model which we called as CDHS, and this is how we implemented the machine learning. It was basically attribute enhanced KNN what we used to generate the three classes over this particular model. Okay. So this is one of the case study. Later on, we again come up with another type of model, which was not multiplicative but additive. It was called a CES model. It was a different thing. I think it will become too much for you people. So this is how we actually develop the exoplanet information. So I hope this is clear to you people. Now I will be discussing one more case study which is very interesting for you people, and I will one or two small videos I will show you for that. So that basically is with respect to something called as gravitational waves. Anyone who has heard about gravitational waves recently? Yeah, anyone here who has heard about gravitational waves? Yeah, it is discovered by LIGO. So what is LIGO? I'm happy some people knows it. Yeah. So what is LIGO, Hemant? Can you unmute and tell? Okay, so let me start. LIGO basically is Laser Interferometer Gravitational Observatory, which basically has two branches. Yeah, it is a laser interferometer, which basically is a device, and it's a huge device. It has two arms. One of the arm is in Livingston, US, Livingston, which is in a state in Washington, DC, and another is in Houston, California. So these two arms basically, whenever the gravitational wave is detected, these two arms basically expand and contract, and with that we define the gravitational waves. Now, first of all, what exactly these gravitational waves are? So whenever any energetic cosmological event occurred anywhere in the universe, it basically produced some ripples in space-time. And these ripples in space-time, we call them as gravitational waves. Okay, so some billions of yeah, you can unmute and you can share your thoughts. So it will be easy to interact also. So what happened? Billions of years ago, two heavy neutron stars were there, okay, or two black holes were there. Basically, they were revolving or spinning far off from each other. Slowly, due to the gravity pull, basically they came together and ultimately they merged into one single black hole. When this merge happened, not much of energy was released, and along with that coalescence, a huge sound has released, and again the ripples have released, and these ripples were in the form of gravitational waves. these ripples actually travel with the speed of light. And when these ripples came to our Earth, it was so light, so many light years away, that it happens millions of years ago. And in February 2016, first time the LIGO actually detected these gravitational waves. Gravitational waves were first identified by Newton in by Einstein. He mentioned about it in his general theory of relativity, but nobody believed him. But later, people started believing when from the first pulsar they received the data, and they got to know that certain cosmological event and some type of wave is coming in. But they could not identify again. Then recently in 2016 in February, basically these events were recorded by LIGO. I would like to show you a small video of that. Just see that particular video, you will understand it very nicely. It's a very good video, which basically shows how these neutrons collided and where we have the gravitational ripples. And after that, I will just start ahead. Just 1 minute. Just let me know if you are able to see or not. Oh, it's telling input cannot be opened. 1 minute. I hope you should be able to see now. Just give me a second. Is it visible?
No, ma'am.
No, ma'am.
Here we can't share our full screen, right? Like we do in Google. Yeah, 1 minute, I think. Okay. Yeah. Is it visible now?
Yes, ma'am.
Yes.
Just listen carefully and see.
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our Sun, were locked in orbit and spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in this system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
Yeah. You have seen this particular video. So what was there basically, how they have made this LIGO detector to identify the gravitational waves. They placed the mirrors actually, and we had one beam splitter in between, which I hope you would have understood what exactly they are doing. So one LIGO arm basically contracts, one expands, then another expands, one contracts. So this change in length basically helps in the identification or collection of the gravitational wave at the detector. So study of the gravitational wave is very, very important because gravitational waves passes all along through the universe, and they carry lot much of information with them. And the careful study, analysis, and investigation of these gravitational waves basically can lead to reveal many more information about the universe. Some of the gravitational waves phenomena is what we are continuously receiving the gravitational waves, still under the consideration, under the study, because these gravitational waves are thought of the effect of Big Bang explosion. So if studied properly, we will possibly also be able to identify what was this particular Big Bang explosion, how it occurred, what was the reason and all. So in order to understand these gravitational waves, its analysis has to be done. Its parameters have to be studied. To study these parameters and to do this particular study again is very, very complicated for the astrophysicists. And this is where again, the computer science engineers are developing algorithms and are helping them. So the analysis of these gravitational waves is itself a huge task. We have, let me show you certain, just 1 minute. 1 second, I'll just quickly take you through. Yeah, if you can see here, we have several applications of the gravitational waves. Okay, what basically we are doing right now through machine learning and all, many probabilistic models, for example, compact binary coalesces. So what do you mean by coalesces? When you have seen in the video just now that when the two black holes collided with each other, the phase when they're colliding and becoming one single black hole, we call that phase as coalescence case, right? So we call it as CBC, compact coalesces, and for this particular thing also it helps a lot. Similarly, we have to have continuous wave search where we are using, you can see where we have papers where we are using various machine learning algorithms and other things for their detection. So we have several of these things. If you want, I will just put this in the chat box here link. You can actually later after this particular session go through this and can go through that various things what you can do with that. G2net is one more library which has been actually developed as a one of the transfer learning model through which we try to do the study of the parameters of gravitational waves. Another one more very big research is going on with the gravitational waves is on the glitch classification. Glitch classification, and we have also recently worked on this, and we have given 1 or 2 papers. I think I wrote wrong spelling. Glitch. So what exactly the glitches are. So when we collect the gravitational waves, you know, these gravitational waves are traveling all through the cosmos. So there are certain other waves also which used to overlap or which used to mingle with these gravitational waves, and hence they basically interferes with the gravitational wave. Yeah, I'll show you the gravitational wave data, how it looks like. So basically they have interference with the what to say, other waveforms, and these other waveforms which interferes, which hinders us with the study of the gravitational waves, we call them as glitches. These glitches are very, very essential to identify. You can say it's a process of noise removal from the gravitational wave if you want to effectively study the gravitational wave. So glitch classification is very much important, where work is again going on. I'll just show you some of the things. Basically, we have HDM5 file, pi file. Just let me open again. Data set. I'll show you first the sleep glitch data. So, is my screen visible?
Yes, ma'am.
Yeah, this is Gravity Spy dataset. Okay, it's a dataset about the glitches. This is in the Kaggle itself. You can actually refer this, and even Zooniverse actually gives you. This is through Zooniverse. We have a citizen science project. I think everyone knows Zooniverse here. You know about Zooniverse?
And me personally, I don't know anything.
Pardon?
So me personally, I don't know about it.
Okay, okay. So Zooniverse basically is a huge repository again, which contains various citizen science projects and data sets where people used to talk, discuss about different things and all. So, you know, these are certain glitches. The glitch data basically looks like this. Kaggle is also providing you these image files. Okay, basically you can download, and they keep on updating also this particular data set, because right now this is one of the what to say, major research area which is going on. Various papers and all are coming in where people have implemented various techniques. Like one paper, basically they have worked on these glitches. They have discussed the use of ensemble methods. Okay, various ensemble methods they have used: soft fusion, hard fusion and all. Base was the SVM classifier what they used over here for this particular purpose, and they got good accuracy. Other than that, many have used convolution neural network, deep learning methods, with which they got some 95-97% of accuracy. That was when they worked with some previous data, and they claimed that they have got these accuracies. One of the paper also made use of the pro-GANs. You know what for we use GANs? Anyone here? What are GANs? Generative adversarial networks. What are those?
So I think like two models are like competing.
Two models are competing, but what exactly do they do?
Okay, I'm not like really sure about it. Yeah.
Okay, so basically GANs have various variants. One of the variant is pro-GAN, which they have used in the paper. GANs we generally use to generate several images. So for example, I just now talked to you about data imbalance showing that particular data set. So in that particular data set, I have very few planets for mesoplanet and just psychroplanet, right? I could have applied SMOT algorithm, or I have used downsampling, undersampling also. So here again, we have various types of glitches, various types of glitches. Okay, but for some glitches we have very less data. For other glitches we have very high data, huge data. Okay, so if I will run my algorithm on such type of data, basically my algorithms actually doesn't give the biased result. And what previous papers we have seen, which I've quoted that they have got good accuracy, this and that, we have recently tested in our own paper. We have just now published and put for a review purpose in some journals. So what we have got to know that these first thing were not balanced. Okay, and what accuracies they were quoting actually are not working on updated data set. So maybe when they executed their models were overfitting. Okay, so it means that since the models were overfitting, they got good accuracies and they didn't tested that. Same time, no paper talked about balancing of the data and all. So that's what we are actually proposing on this particular glitch data set, where we will be actually looking ahead, applying some other techniques for the data augmentation through some different types of GAN. And we will then apply our deep learning methods or technologies, or maybe some other technology, machine learning technology, through which we can easily identify these glitches. So these glitches are huge interest, and gravitational wave study is very, very important presently. So here we also have gravitational wave data. So you can see here G2Net is a recent library which basically has been generated. This is one notebook which has been opened. So we have data set also. Let me just put it here. So what I showed you actually here in the Zooniverse, we have used data sets. So these are different types of glitches, blip, whistle. One category, since they are unable to identify most of the glitches, they put it into none of the above category. So on that also more work is going on. So we have several glitches. So if you will go to collect, you can see here gravity spike collections in this, and it is showing you different collections. So these all are gravitational glitches images on which work is going on right now. So before studying, its pre-processing is very much required. And for that purpose, right now, recent work is happening in this particular direction. Then for its study also, we have various models which are coming in, like G2Net is one such transfer learning model, which has been introduced in order to detect continuous gravitational wave. So if you people also want, you can actually start exploring these data, exploring the things ahead. Okay, just see some of the work which is being already done, read some papers related to that. You will get a good idea on these particular things. So these were the main two categories which or case studies I should say today, which I wanted to discuss with you people. I hope you would have got some knowledge. Other than that, we have actually various other approaches, like various other fields in the astrophysics domain. Like we have still issues with the galaxy identification. Many galaxies from far off, they look like a star or pulsar or quasar, because quasars are the brightest celestial object, and galaxies are also very bright in the sky. So both look similar when you see from your telescope. So again, it's like very much difficult to identify a galaxy. So galaxy identification is one such problem. And if you will meet any astrophysicist and all, they will tell you many more such problems. We have also worked on star galaxy separation. So we have various supernova classification is still a problem, people have done the nova classification, but supernova still, we have type 1, type 2 and all. It is very difficult to identify their types basically through the hydrogen spectrum they used to identify, which is very complicated for the astrophysics physicists. So they are still looking for good approaches, good techniques through which with confirm they can actually do. Diffusion models over GANs. So yeah. So diffusion model also we have actually tried. So that also didn't work. We have GANs various models also right now. Diffusion model also we have tried, Aditya. Yeah, thank you so much. So for impedance models, yes, diffusion model is also one very good approach which we can actually use for the balancing. But still diffusion models are also not working very good on the type of data what we are using right now. So we have actually identified a different variant of GAN, which we are working on. Yeah, I hope any questions and all.
Members, if you have any questions, please feel free to ask, ma'am. Ma'am, we have received other questions, so I'd like to ask them. So the first one is, physicists say aliens may be using black holes as quantum computers. What is your opinion about this?
Yeah, this is actually from certain German philosophers, what they have actually told like that. See, people think that if aliens are there, why still there is no discovery about it? We have the SETI project on for this, right? So it's not exactly they say like that, but we don't know in what form life will be existing. Who are actually these aliens? Are they really having extra intelligence than human beings and all? Are they doing less activities and all? See, actually, if you see, like I talked about today, one metric ESI, Earth Similarity Index, based on which we developed our own different metric. So we have for the biological complexity also we have an indices which we call as biological complexity index, BCI, biological complexity index. So it's the existence of life in some form, right? So as you would have seen movies like what is that Hrithik Roshan movie? It was on aliens and all. That Jadoo wala movie, I forgot the name.
Yeah, कोई मिल गया.
Yeah, koi mil gaya. So, see, we don't know whether the life exists like that or it might be small microbes or something like that also. So, life can be in any form, right? Need not to be a particular type of life where maybe liquid water is necessary for them to survive, right? They may have some other conditions, some other type of things. So, we actually, thing is that they say all these things, but we exactly till now we have not seen any such life so far. However, on Mars, if you would have seen through Mars rover exploration, we got to know that there were some little microbes existing over there. And that's how they started the search for the liquid water over there, because they thought that this type of microbe can only live in water. So that's what basically we can say. Still, these questions and these things remain question mark, right? So people are working on various things. Drake's equation, also if you would have heard about, Drake's equation also has been derived. So that particular equation is basically to find the number of technological species that have formed over the history of the observable universe. It means that what we can see over the years, how many types of species we have seen just now, and it is basically the product of number of habitable planets, right? for the given volume of universe multiplied by the likelihood of you can say species which are arising as one of these planets. So on that particular planet, how many species have been that multiplied? This is what the Drake has given the equation to find. But who knows in what form the life is existing, right?
Yes, ma'am. And this is another question. I believe it's interesting. So, someone has asked that Elon Musk says that we are probably characters in some advanced civilizations video game. So, like, what do you think of it, ma'am?
So what exactly you told? We are probably
Uh, Characters in some advanced civilizations video game.
okay. Yeah. So again, we don't know, everything is getting digitized, right? So where we can see in the coming future, near future, how we also are going to be on this particular earth. Yeah. So on this particular earth, we don't know how it is going to be the near future, right? We are listening that one solar flare is about to hit the earth in 2025. So if that happens, it's a very huge solar flare. And if that flare hits the earth, then earth is going to burn. We don't know what kind of life will be there after we all go, or if sun's core will be over, what is going to happen. So we cannot answer such type of questions, which basically we don't know who has seen tomorrow. So yeah.
Like one question, like when the solar flare hits, like I think it's the Earth's magnetic field which protects us, right?
Yes.
So like this one will be more powerful. So
yeah, that's what we are listening, that this particular solar flare is going to be very powerful, and majority of the earth is going to be
okay.
Yeah.
Okay, yeah. Okay, that is scary. So only 2 more years.
Yeah, we don't know who see, like people are working on that aspect also. NASA has launched its spatial satellite to read that data only from the sun. We have solar physics, again a different area in the astrophysics domain, where people are working, they see the activities which are happening in the sun, right? And because it is our star, our own star, how it is going to affect us, right, at various point of time. So recently, yes, this has been predicted by NASA. Yeah, I need a technical question.
Ma'am,
Yeah.
ma'am, can you give me some insight on use of computational astronomy in studying dark matter halos?
Use of computational astronomy
In dark matter halos, you know.
in dark matter. So I have not much explored within that particular area still. But see, computer science is now everywhere. You go wherever. Actually, astrophysicists are actually working on telescopic data. We have what to say, various high resolution telescopes now, like LSST and other types of good resolution telescopes, where you read only just the pinch of tip of your like fingertip part of the sky. Also, if you are reading, you are going to get tremendous huge amount of data. And data analytics is something which is required everywhere. So see, data analytics is a part which astronomers also can do. Okay, because data analytics is basically related to the statistics. So statistical part solving that they can also do. But what analysis you are doing to develop algorithms for that, right? Similarly, to develop new models for those particular things so that fast you can do the study. That's where basically we, the computer science engineers, are working in these particular domains. You have like that several domains where now we are actually into the but we are into the banking domain, we are into the finance domain, we are into the healthcare domain. So every domain we are there. So how we are helping them? What is exactly their problem? Understand the problem carefully, go through the deep insights of that, what they want, what are the type of input they are getting. Then you have to work on that to develop, to ease their work. so that things can be done in a less complicated way. So you have to work on those particular aspects. So I would like to say the entire community over here, student community, that we generally use the tools, right? So instead of using the tools, just focus that how we develop our own tools. So for that, you have to be very good in algorithm development. You have to be, say, for example, we are using already existing techniques, right? Like GANs or some machine learning algorithm like SVM, SVR and all, right? Similarly, we use artificial neural network and other neural networks where we use already developed neural network activation functions and all. Can I develop my own activation function? Can I develop my own algorithm for doing this? So that should be our focus now. Basically, most of the time we see other researchers which are not like in India, they do more work in these areas. So whether it is dark matter, whether it is exoplanet study, whether it is galactic data, supernova data, we have to find such type of computational, we have to devise such type of methods, we have to give a thought process for that. So we should be very good in our concepts and everything.
Okay.
Yeah. Yeah. Any other technical questions if you have?
Ma'am, another question is, how can we as students enter into this interesting field of astronomy and computing? And what are some major research avenues?
Yeah, so I think one or two major research avenues where research is going on, I already talked to, right? I think gravitational waves is one very, very recent topic on which people are actually working in. Then how we discussed about ESI, like that I told you people about biological complexity index and all. So on these aspects, still research is going on. So what I will suggest that those who are interested in this particular domain, they should collaborate with certain people who are doing research in these particular areas, right? So you should be knowing like who are the faculties working with you in these areas, or who are the people across the India who are working in these particular domains. You better contact them, tell them that you are interested in doing such type of projects and things related to that. Then I also showed you certain links here, right? Zooniverse, some of the citizen science projects related links and all. So what you can do is that you can actually start working on your own, also read good research papers, which will be giving you an idea what people are working on. You will get a clue. Okay, I can improve on this. I can do more on this. So like that, actually, you can start entering. Once you will enter, you will publish few papers. Automatically, your name will be there. I think better will be that you people initially at this stage, as a student, collaborate with certain good faculties who are working in these domains. So you will get a better idea on these things. Yeah, anything else?
Ma'am, you mentioned Zooniverse as a citizen science project area. Are there any, can you mention other websites also?
Yeah, we have several. I can actually give you people the links and all. So if I will be mailing it to Vishak, so will it work? If he
Yes,
can
ma'am.
with all of
Yes,
you.
ma'am.
Yeah, so we have certain more good resources available. So where you can get the data sets, you can get the problem statements also, where you can actually start working. I hope the session would have been interactive for you people and informative mainly.
Yes, ma'am. Like I joined late, but it was very interesting.
Okay. Any other questions and all you have? Okay, so What I will do, I'll give you some, I will just give certain good data set links, data source links, and some good tutorial links wherein you can explore different problems in this particular domain. And then you can actually start working on these type of things. We have nuclear physics also, quantum physics also. All these are related to the astrophysics domain actually. So you can work on the biological side aspects of this. You can develop the algorithms for the light sustainability and all. Similarly, we have some other also things like that. I'm also presently working on one another project which is basically related to the climate change model. So we have several such type of multidisciplinary aspects and all. So later on, I will share the few things with Vishak. So I think better he will be sharing with all of you today.
Yes, ma'am. Thank you so much, ma'am. We have come to the end of the session. I would like to take this moment to express our gratitude to our esteemed guest speaker, Dr. Surbi, ma'am, for sharing her expertise and insights with us today. It was an engaging and informative and, of course, thought-provoking session. Thank you, ma'am, for taking the time to share your knowledge with us.
Yeah,
I'd like to thank you, ma'am. I'd like to
Thank you so much,
participants
ma'am, for
here
joining
today.
us. Yes, please continue, Pooja.
Can I leave?
Yeah. Finally, I'd like to thank the members of the team.
Yeah, thank you so much. Thank you so much, all of you. If you have any other queries or anything else, you can connect to me with Vishak, and if you want, I can help you out for a few things. Be very good. Nice.
Thank you so much, ma'am.
Yeah,
Yeah.
thank you, ma'am.
So guys, please do not leave the meet. Ma'am, like you may leave. We have some other updates to make to the house. Yeah.
Sure. Thanks.
Thank you so much, ma'am, for joining.
Thank you, ma'am.
Thank you, ma'am.
So like today we have conducted the elections for the Deputy Secretary of Nilgiri House. So I would request Lakshmi Nandan to declare the results.
Yeah, so the results of the so we have analyzed the results, and so we found that the winner of the election has won 41.1% of the vote, and that person is Abhishek Dikshit. I repeat, that person is Abhishek Dikshit. So yeah, congratulations to him. So he'll be a new deputy secretary.
So Abhishek is our new Deputy Secretary for Nilgiri House, but we will also have a core committee, which will also comprise of Amit Vikram, Rushil, and who was the other guy?
Akash Rajke.
Yeah, and Akash. So we will actually form a core committee for Nilgiri House comprising of me, Lakshmi Nandan as the web admin, Abhishek Dikshit as a deputy secretary, Amit Vikram, Rushil, and Akash as the core committee members. And we also have with us Swati, Pooja, and some other guys as a web admin. So this is the core committee for Nilgiri House. We would also like to invite all of you to be volunteers for any of the events coming forward. So you all can host events. You all can even form groups under Nilgiri House and manage those groups, such as like we can collaborate to form coding clubs and other clubs. So if you are interested, please do let us know. Like you can DM me or mail me at nilgirisec@ds.study.iitmadras.ac.in. So with this, we would like to conclude. Thank you so much, Pooja, for hosting this event. Thank you, Lakshmi Nandan, for the posters and for organizing the entire event. Thank you, everyone. Thank you for joining.
Yeah. Bye-bye, everyone.
Thank you so much, guys, for joining.
Thanks, everyone. Have a good night.
Hey, those links which ma'am will send, you will send to our mail IDs, right?
Yeah. So one thing, like those who are interested to get those resources, please I am sharing my mail ID. 1 second in the chat box. So you all can message me. I'll share it to you, all of you.
Yeah, I think we have people outside Nilgiri, right?
Yeah, so like I'm just mailing them my email ID.
Yeah. So yeah, I don't think it will be possible for you to like mail everyone.
Yeah. Like we're not allowed also. So
Yeah.
guys, you can mail me at nilgirisec@ds.study.iitm.ac.in, and I'll share all the resources that ma'am would share with me.
Yeah, like has everyone noted this email down?
Yeah.
Okay.
Thanks, Hemant. And thank you guys for your attention throughout the event and for engaging with us. We are really thankful to all of you.
Yeah, I guess we can like close the meet or recording or live streaming.
I think the live streaming is still going on, so
Yeah.
We can just leave them. That's it.
Okay. Yeah. So I'll leave then. Maybe let's wait.